content of this week's session. I'm going to go through digital and analog input and output devices and their signal types. Going to look briefly at how PLCs process analog signals. Those two things will help with your assignment. And then we're going to look at document and GX developer programs. So the full exercise is in last week's notes. I'm just going to briefly go through how you do that documentation on the screen, make some pointers about it. The idea of the exercises that you go through and document the solution to the double coiling exercise that you did. Okay, and then I'm going to look at doing a brief introduction to and helping you get a good start on the first real programming exercise, which is programming the pedestrian crossing traffic lights. From next week onwards, the session is going to turn into a lot more practical and a lot less listening to me up the front here. Okay? So, yes. No, but the idea is that you practicing the programming skills. Those that can already do a bit are going to go through that a lot quicker and maybe do some other additional bits and pieces. Very much in this module, it's not just about teaching you what you need to do to pass the assessment, it's about how much extra you can learn about programming PLCs. So I've got plenty of things up my sleeve, but I won't be issuing assignment 2 until after the break, whatever happens. Alright? So, digital input devices. Well, digital, the very nature of them, means that they can only have two states. They're either on or off. In old parlance, logic 1 being on, logic 0 being off. Okay, there's a number of different ways people talk about it. Normally the off state is represented by 0 volts at the input terminal and the on state represented by 24 volts, for example, dependent upon manufacturer. However, like anything in life, they all have their tolerances. So the specification for a piece of kit has a nominal 24 volts for an input, but it could be that they have to allow for a tolerance on those values. So if we look at the specification for the PLC input, what they'll do is say anything, for instance, between 21 volts and 24 volts in that area will be recognized and will turn on that PLC input. Anything lower than 3 volts, for example, and that PLC input will recognize that as off and turn the input off. In this area here, we don't know what that'll do, is what the specification is saying. Okay, it might accept 0 being slightly higher than 3 volts, but the specification says if it drops to 3 volts or less, we guarantee the input will turn off, and if it goes to 21 volts or more, guarantee it will turn on. So a manufacturer of an input device, let's say an electronic eye or a capacitive proximity sensor, needs to make sure that it outputs voltages when it wants to turn it on that are greater than 21 volts in this area. So that line is greater than 21 volts and it comes in up here somewhere above that line, and this is guaranteed to be less than 3 volts, so it comes in underneath that line. If you do that, then that input device will work with that PLC input. Yep. But the key thing here is digital means only 2 states, on or off. And computers cannot recognize anything else other than simple ons and offs. We do more complex things by combining lots of ons and offs together to represent more detailed information. So we're all happy with that as regards to the basis of what a digital input entails and the nature of those signals. Different input devices. I know I had to move this morning, so I'll do it now. Mechanical limit switches. Range of examples in that picture there. Any ideas for advantages? What do you reckon? No ideas at all? Advantages of mechanical style switches, push buttons. Surprised I haven't got this one. Yeah. I'm going to put maintain on there. In terms of, usually you can change the contact block. So if the contact block goes, you can change parts of them. You can put a new wheel on them, that type of thing. Okay. Disadvantages. Two main ones. Mechanical life. They have a mechanical life. So they have a finite mechanical life. The wheels can break, the contact blocks can burn out, that type of thing. They're only good for so many, a million operations, which sounds a lot, but automated machinery moves quickly and can quite quickly use that up. There's one more major one that really needs to be considered, and that is this. Requires direct contact. So, and I'm saying that's a disadvantage, is in some applications. If you're trying to count quite light product moving along a conveyor, you're going to knock it over if you've got anything like a limit switch, just direct contact. Yeah? Doesn't matter on a big heavy piece of moving machinery. You quite like the positive fact that you can see that it's making contact with the wheel and actually moving it. So there's fors and against that, depending upon the application that you're using it for. So there are some areas that you might want to think about if you're going to talk about the advantages and disadvantages of those. Then we've got capacitive proximity sensor. These can sense the presence of metallic and non-metallic objects. Okay, so they'll detect plastic, ceramics, metal, most objects. Advantages. Yeah. Non-contact. Yeah. Anything else you can think of? Yeah. No moving parts. What about disadvantages? Cost. Yeah. because it's not necessarily just the disadvantages against mechanical, disadvantage against other electronic methods. Limited range. Yeah. And then there might be others. One thing about all the fact, the whole electronic sensor thing, is the massive wide range of different styles and specifications that you can get. Choosing the right one. These things have different modes of operation. Does it turn the input on when you cover it and off when you take it away, or does it turn it off when you cover it and the input comes on? So normally open and normally closed modes. Some offer both in the same sensor. You just change the way you wire it. Okay, different power supply options for it, whether that's NPN or PNP that we talked about the other week. It just seemed to be a minefield trying to decide whether, particularly if you're trying to replace something you've already got, and you try to choose something that's going to work in the same way, but that's not available anymore, so you're looking for a direct replacement. It's a bit of that's quite a minefield trying to find the right one. On the next page, we have inductive proximity sensor, able to detect the presence of metallic objects. Yeah, so these don't detect plastic. That way, if you can use a capacitive and an inductive in combination to distinguish between plastic product and metal product. I'm not saying that's a metal detector, but it will. Using the two sensors, you could discriminate between two different materials, metallic and non-metallic. Yeah. And all I wrote this morning, and I plan to do the same thing, is similar, add, disadvantage, with capacitive. They are non-contact, they have a limited range, they're relatively more costly than mechanical solutions in many cases, and so on. They're very similar. Okay. What we then move on to are photoelectric types. These solve the issue with the capacitive and the inductive over sensing distance. I've never seen a capacitive or inductive used to sense more than sort of 4 or 5 centimeters away from it. They are adjustable. These things I've used from here to that filing cabinet easy and further. There's optical things. The only issue about that is actually getting the alignment right, either with the reflector or with the transmitter-receiver pair. Because there are 3 general types. The first one is diffuse. And if this is the object you're trying to sense here, choose a different colour, then what happens is a transmitter in the sensor sends out a light beam that is then reflected back, okay, when that object is in front of it. And you can adjust that distance so you discriminate between objects you don't want to sense further over this way, okay. But the unit contains a transmitter and receiver in the same unit, and the reflection is actually off the object. But then having that reflection might either turn the input on or off, so you've got those normally open, normally closed options again. And on most of these sensors that is selectable, and then you can have NPN, PNP types and so on. Second type is where you have a separate reflector, like the sort of thing you'd see on the back here that makes, like on a road sign to make it reflect, a prism style reflector, that when the thing is not covered, it transmits out to that reflector and back again, but when you cover it up, you block that return. Yep, so here's our object. Our object is between the reflector and the transmitter-receiver combination. And then the last type is where we have, so these are T stroke S stroke R, transmitter stroke receiver. Here we have a transmitter and a separate receiver, and then your object blocks that through beam between transmitter and receiver to send. They're probably the ones that work over the longest distance, but most difficult to set up, trying to get the two units of transmitter and receiver directly aligned up, down and left and right. The honest answer from me to that is I don't know, but infrared I would think. Not visible light in most cases. Ones I've used. You got any that got visible light? The light curtain ones do sometimes have. If they're like the safety light curtains, but these ones can't see anything. So you can't look for like a spot or a dot on that reflector because it isn't there. You kind of got to just move it until or use a piece of string to get them lined up, that type of thing. Or a straight edge if they're close enough together. Right? So they kind of get round this distance problem, okay? They can be affected by moisture, dampness in the air. You guys are in a food factory, so you probably know about that. You know, lenses get steamed up and that type of thing, so they can be a bit problematic. There might be newer modern ones right now that don't get affected in that way, but I know when I worked at a food factory, that was kind of a bit of an issue. Okay, with the plastic bottle thing, the issue is around how well it can sense clear plastic in terms of the fact that the beam can go through the clear plastic, but you want to sense it. So there's set up sensitivity issues around that. They'll all work really well with a nice opaque colour block coming in front of them, but when that's something that can actually allow some light to go through, they're a little bit more tricky to set up. Right, I'm going to move on now to look at just a very brief coverage of how analog inputs and how a PLC deals with analog signals. If we consider the case where you want to monitor the level of water in a tank, what we could do is put level switches in at all the different levels we wanted to sense. So the more switches we put in, the more indication we got of the actual level in the tank, but there's still an error between them. So we could put another one in between here and another one in there, and we'll have quarter full, half full, 3/4 full and full and empty. We could put them then again between them, but every switch we have needs an input on the PLC. Yeah? Okay. There would be something we could do about that. We could do what's called multiplex it, so that we look at how many of them switches are turned on. We wouldn't need to use so many inputs, but that's a separate issue. The analog situation kind of gets rid of that problem, not totally, but it gets us away from that. Okay, so what we can do is, in place of the level switches, insert some kind of level sensing device in the bottom of the tank or the top of the tank. Mostly what that would be is a pressure sensor, because of the relationship between the height of the water in the tank and the pressure at the bottom of the tank. So that has nothing to do with the width and length dimensions of the tank whatsoever. It doesn't matter if that's just a pipe or if it's a massive tank as big as this room. The pressure at the bottom for the same height of water would be the same. Yep, so this is a pressure sensor that varies between certain levels, 0 psi and let's say 10 psi if the tank is full. Okay, what that does is gives us an output of typically 0 to 10 volts, 0 being tanks empty, 10 volts being tank full, or 4 to 20 milliamps. 4 milliamps is empty, 20 milliamps is full. It's really kind of beyond the needs of this module, but does anybody know why 4 to 20? That's what you got. It's got a positive 0 level. 4 milliamps represents 0, because then in that current loop, if you measure it and you've got 0 amps, that means the loop is broken. You've got a fault. So the positive 0 there indicates immediately that there's a break in that feedback loop, in that loop from that sensor. You've got an open circuit. Because even the lowest signal you should be getting is 4 milliamps. So it's quite a very common signal level to use in instrumentation is 4 to 20 milliamps in control systems. Your Mitsubishi PLC, certainly the FX models, we've got some analog boards, and they will take either 0 to 5, 0 to 10 volt, or 4 to 20 milliamp signals selectable in software. So depends how you program the setup of that analog card as to what type of signal that's going to take. And how you wire it, of course. So when we talk about analog signals, we're talking about something like this. So here's our full, empty of our tank, and we got a signal up to 10 volts. When I ask people students about the nature of analog signals, what they often say is they're a signal that's constantly changing. That isn't true. What they are is a signal that varies anywhere between two limits. These two limits, 0 and 10 volts. So that signal can be any level, can be 2.356 volts, to be 7.382. Doesn't mean that it's varying all the time. It can be varying, going up and down like this, for tank levels going up and down, but equally, if nothing's going out and nothing's going in, it's at some stationary point between those two limits. But the key thing is, it can represent every single possible level in that tank, between full and empty, and the nature of being somewhere between 0 and 10 volts. Yeah? So, having gone through that, how does a PLC deal with a signal that can be between 0 and 10 volts? Because a PLC can only actually understand ones and noughts. To handle analog signals, what it needs to do is have a separate analog input module that can it uses an electronic circuit called an A to D converter, an analog to digital converter that takes that 0 to 10 volt signal and turns it into a binary number of a certain number of bits, or a binary word of a certain number of bits. So for example, if I input interface and I've picked a 15 volt level signal because it fits in nicely with 4 bits. If we had a 0 to 15 volt signal, a 4-bit binary word can represent 2 to the 4 or 16 different voltage levels. So that'll cover 0 to 15 volts, with 0 volts being represented by the binary number 0000, and 15 volts being representing the binary number 111. So there's 111 all at the top there. There's 3 noughts at the bottom, and they go up like this. I'm not going to do them all, and so on. Okay, This being the units, or the single number at the end. That being on represents 2, that digit being on represents 4, and that digit being on represents 8. So when we get to the top there, we've got 8 plus 4 plus 2 plus 1. Yeah, 15. Okay. However, 7 volts here is represented by 111. So that's 4 plus 2 plus 1 makes 7. Do you see how a computer represents numbers larger than 1 as via a binary word? If you've done any software engineering, you'll already know that. But in terms of this representing this signal, it's only going to be able, with a 4-bit word, to represent this 15 volt signal in 1 volt steps. And the error created, to anything between 0 and a volt, you've got a 1 volt error in each of those steps. That's called a quantization error. And anything that involves digital to analog conversion is going to have at least a small amount of quantization error involved in it. However, we can reduce that step size by increasing the number of bits we use in our word that represents that signal. If we upgrade to typically a 12-bit word, we can represent 2 to the power of 12 different steps, which is approximately, not exactly, but approximately 4,000 different voltage levels. That would mean our 15 volt signal would be represented in approximately steps of 3.75 millivolts, which is a lot less than a volt, the error that we had before. If we go up to a 16-bit word, we then got 64,000 combinations in our binary word, and therefore our 15 volt signal could be represented in 230 microvolt steps. So our quantization error is considerably reduced each time we add an extra bit to the word that is involved in representing it. For obvious reasons, the D to A converter that sits inside that module becomes more and more expensive as you add more bits to it, and the processing power needed to process all of that data becomes more onerous. So you then need a faster processor to handle, and a more complex processor to handle the larger word size. Yep. So that's analog inputs. If we want to think about analog outputs, for example, one might be used, you've got a motor speed controller that requires a 0 to 10 volt input to control the speed of a motor between 0 and 3000 RPM. What we could do is have the PLC represent the desired speed of that motor in the form of a digital number, similar to the binary word for the input. So the PLC decides how fast it wants the motor to run. It turns that into a binary number between top and bottom limit, and then it outputs a signal according to that number between 0 and 10 volts. So it's kind of just the reverse of the analog input. Inside that module, this time there's a digital to analog converter. It converts that digital word to an analog signal between 2 limits. So it's kind of just a A to D converter flipped the other way around. Again, you might find ones with 0 to 10, 0 to 5, 4 to 20 milliamp, and so on. They might even be able to handle a selection depending on the way you wire them. In fact, our analog cards on our systems, I think have got 2 analog inputs and 1 analog output on that card. So it just depends on what you buy. Okay. Are you all reasonably happy with that coverage of different input types, analog and digital inputs and outputs? Yeah? Right, what I'm going to move on to now, and there is some more, in your last week notes, there's a more detailed step through of how to do this documenting, so you can go through and document your program that you wrote that solved the double coiling problem, just as a way of practicing the techniques. It shows you how to edit these. I'm just going to go through them on the screen here. So, careful program and documentation, invaluable when it comes to fault finding. Even if that's a program that you've written yourself, if that's complex in nature, come back to it 6 months later, there'll be parts of it that you might not understand as well as you did when you wrote it. So good documentation and commenting is invaluable. GX Developer allows for a number of elements in the ladder diagram to be commented on. You can have rung statements. They are these. So the idea of them is they can be multi-line statements describing what that section of the program does and how it works. Detail you put in that will depend on how complex that particular rung is. It can have comments. They're these green comments associated with each of the elements in the program. So this one's associated with X002. It's the switch to start the cycle. Okay, what that is 4 lines of 8 characters. However, the full comments take up what I call screen real estate. If you have them turned on, you can't look at so much of your program on the screen at one time if you're monitoring. So you're likely to want to turn that off and on depending on what you're doing at the time. And you can do that. Okay. Then the last thing is the alias and the device name. So here we've got T1, and it's got with it a short alias. Maximum 8 characters, no spaces allowed. And what I tend to do is kind of come up with a method of writing a short alias. The example at the bottom there, PB, PMP on, push button, pump on. And if you're consistent with the kind of way you do your things, you'll create a kind of a little short name that's understandable to you in most cases when the full comments are turned off. Yeah? Now, if we go and look at the program, and I'm not going to spend time actually editing it here too much, because I've done that this morning. First of all, the aliases can only be edited in this comment area over here. They go in this box here. Now, when you first go into this screen, right, where was I up to? Yeah, I was doing this drop-down box. Because I've already entered some, there's entries in this drop-down box for timers, outputs, and inputs. When you first go into this area, that defaults to X0 and all the inputs. And none of the others are in the drop-down list until you request them. It's a bit of a foible of this program. So if I want M relays for the first time, I've got to type M0 in there, and then they come up, and then they'll also be available in the selectable list. Okay? So in here, we can type in the full comment if we want to. Okay? Just going to take the spaces out of there that I've put in, and I'll show you why that happened. Over here is the short alias. Remember, that can't have any spaces. I always tend to make my aliases capital letters, but just a personal preference thing. But I don't do capital letters in this area. I'm liking it to showing at people. Okay, so you can edit both of those in there, and I've also done a couple of timers and so on. Yeah. Go back to your main program by double clicking there. What I then have to do, the default, let me turn this back to no alias, no statement. Right, so that's where you are until you turn on, first of all, the full comments. Notice how that's taken up more room on the screen now because the comments are turned on. Also, if you look at this one that I changed back, this one here, that's split the word system. It's got S on the top line and then the rest of it's on the next line. It's not formatted very well. And it's actually easier to get those looking right if you edit them on the ladder diagram. You can do the statements and edit the comments on the ladder diagram. You just go into this mode, comment mode, double click there, you get this dialog box up, and this actually gives you an idea of what it looks like on the screen. So I can now go in there and I can put a space in there to push system properly on the next line, and I can put a space in there to get the on the third line, and then that's tidied up. And you only need to edit one version of it and then all the others update to go with it. Okay, so that's the full comments, but it takes up more real estate on the screen. So I'm going to turn them off like so. The other thing we want to do is turn on the alias. Okay, now by default it will come up when you do it by default like that. That's with the alias replacing the device name. Not really that helpful because it tells you that input is switch on, but which input is it? Is it X2, 3, 7, 98? Don't know. So that's what it does by default. What you actually want is where it was in the first place, arrange with device and display, not replace. Now we've got both. We've got the alias switch on and we've got the X2, so we know which terminal number it is in our panel if we want to test for 24 volts. Yep. And then lastly, we've got the statements. So if we turn the statements back on, they are the multi-line explanation of what the ladder rung does. You edit them in statement write mode, and I double click here, I can put a new line in like so, and I can have multiple line statements. Yep. So there, in last week's notes, like I say, there's a step-by-step exercise that takes you through all of those steps on that program that was the solution to the double coiling problem that we went through last week. Okay? Notice that statements need to be accepted or upgraded. It grays the line out. Everyone reasonably happy with that? Right, last thing I'm going to do with you with regards to me talking up here today is just go through, and when you're ready to do it, I'll give you a separate sheet. You've already had some detailed information about the pedestrian crossing task, but I'll give you a one-sheet explanation of what the program's got to do, what the inputs and outputs are. I'm going to take you through a little bit about how to get started on that program, step by step. The idea is then you go on and you actually program that bit, check that bit works, and then finish it off to the full specification. It's your first attempt at programming a real piece of kit. So the first thing you've got, the first piece of information you've got about this is that there's a standard set of lights with red, amber and green, and then the pedestrian's got a crossing's got a wait, a walk and a don't walk light, plus a push button to request a crossing. Yeah? And then you've got a table that tells you that the push button's connected to X0, and then the green light's Y0, the amber light's Y1, and so on. So it's got an input and output listing. And that would be part of any documentation for any system that was controlled by a PLC, would to say which output does what, which input does what. Okay? You're then on this task here, the next bit is a full run through of the traffic light sequence, what the time delays are between each change of light, and so on and so forth, to tell you what the specification for the program is that you've got to achieve. And if I go on to the next page, I've taken a recommended strategy for writing a program is to work through each bit of the specification step by step from the top and testing each stage as you go along. Does that do, up to that point, what the specification is? Now I move on to the next bit. You might sometimes have to go back and change something that you had working, but you need to know that bit's working before you move on to the next bit. Then any problem is a small one. If you go and write 10 lines of code all in one go, thinking that's going to work and solve the whole problem, you might have 12 bugs or errors in your program to solve all in one go, and they're all interacting with each other. They're all causing multiple problems. Whereas you start from a good base, I know that bit worked, it's not working properly now, it must be something to do with the changes I've made. How can I modify those changes? Yeah? So, it's not the only way, but with a defined sequence, like the traffic lights, red to amber to green, back to amber to red again, with the wait and don't walk and all that in between it as well, okay, it kind of fits well with having an M relay for each of the steps in that sequence and getting it to step through those steps one by one and use the M relays to control the appropriate lights at each step, dealing with like state changes of the green light, for instance, state change of the amber light as you go from step to step. Okay, so what I've done with the group this morning, and I'm going to do the same with you, is go through how you might tackle the first couple of steps and filling in a sequence chart that describes exactly what each step does. And that don't fit every kind of task. The next one that I give you, the motor forward reverse, is kind of something that's a bit more got two different decisions about it, and that's not a defined sequence. So it don't fit so well with this method. You can still do it one step at a time, but it's not a defined sequence. So, the first part of the specification is that on placing the PLC into run mode, you can use M8002 as a special function relay that closes for one scan time the moment you flick that little run switch on. So you can use that input to initialize your lights into the starting condition. Initialize step 0, I've called it, of my sequence, the base step. That step is where, on placing into run mode, the green traffic light and the red pedestrian don't walk light should be turned on, and then that's going to sit and wait for somebody to come along and push the button and start the sequence. So the initial condition on switching to run is that the green traffic light comes on and the red don't walk light comes on. So that's the first step in my program. Step 0 is associated with the M relay. M0 is going to be on when I in that step. It started by switching to run mode. I've put an OR in there. Okay, you're going to find out why there's an OR in there later on as you're programming this. Okay, it's ended by the fact that step 1 comes on. M1 is step 1. So when step 1 turns on, it cancels step 0. You're only ever going to have one of these M relays on at a time. Makes it easy to fault find, because when it gets stuck somewhere, you can find out why it's stuck at that point. And you only got one little bit to look at. What does that section do? It starts a timer. No, it doesn't. That's a typo. It latches M0. So as soon as you turn it on, you're going to latch your M relay. Okay. Then what you're also going to do is turn on the green light and turn on the red don't walk light. So those two are going to come on. The rest of the lights stay off. Okay. Now, if I go on to the next page, that's what it goes in there, the action. Latch M0, wait for X0. So it's going to just sit there and wait with those two lights turned on. Okay? And we use an M8002 as the one scan cycle pulse to turn that action on. I think on the next page I've got that kind of programmed, yes. So, something to look at here is, as I'm already starting to structure my program into two distinct areas. Above that blue line is going to be my program steps, M0, 1, 2, 3, 4, however many there are. The control section, if you like. Okay, or sequence section I've called it. Then below that blue line is the output section. So that we don't double coil, we're going to always control our lights using these M relays. So here's my first program line. I've got a normally open on 8002. I'm going through a normally closed on M1. That's what we said is going to be the element that turns off this step. That's going to turn on that 0, and it's going to latch itself. Okay? It's going to sit there and wait. And that M0 instruction is going to turn on there and there and turn the green and the don't walk lights on. That's the first stage of the program. Write it, test it. As soon as I turn it to run mode, do those two lights come on. And the next two pages, I think, detail what's going to be like. When you upload your program and you're out of run mode, all you're going to see is that element closed because M1's turned off. Nothing else will be lit up. But as soon as you go to run mode, it's going to pulse that so quickly that you don't even see it, which will turn that on. That's already closed, so it'll latch through that M0 contact there. These two will turn on, and those two will be on. That's that bit done and tested. We then have to do is move on to the next section. So, M1, step 1, started by somebody pushing the X0 button. Ended by M2 being turned on, the next step in the sequence. What does it have to do? It has to latch M1 and it has to start a timer T1 set to 10 seconds. It also has to make sure the green light stays on, the don't walk light stays on, and we got a state change for the wait light. The wait light also comes on. So as soon as someone pushed that button, the visible action is that the wait light lights up. And behind closed scenes, invisible to the person that pushed the button, a timer for 10 seconds has been started as well. So then we got to program that line in the program. So that's what we already had. So I'll look on my next page. What we then do is we need to start thinking about inserting lines in between. So it's the notes that you've got will take you through that. What we're looking at doing here is, here we go. So step one, if we look at that step, someone pushes the button here, turns on M1, latches itself through M2, and we're also turning on a timer, T1, for 10 seconds. So that is that step in the sequence. Okay? And I've inserted that after the first step, but in front of the output section to keep that structure going. So if I can look at outputs, or I can look at the sequence as a separate entity, and I've got some kind of logical order to this program. Looking a bit further down, so that's the sequence bit of it. So what's going to happen as I turn on, that bit's going to go, someone pushes the button, latches this, it starts to time. What I've also got to do is make sure I put an OR instruction with M1 to keep the green light turned on. I put an OR instruction on M5 to make sure that the don't walk light stays on in that step. And I put a new ladder rung in there between the two because I'm keeping them in number order. M1 is also going to turn the wait light on. And if you think about it, just this step sequence is going to be a copy of that line with some of the numbers changed to get the next piece of functionality to work, and add an OR statements in the appropriate output line down the bottom so the lights work. Yeah? But the key thing that you're going to have to work out at the end is how do you get it to step from the last step back to the step 0 again when you want it to go back to the green traffic light and someone waiting for someone to push the button again. So what makes it step back to step 0 is the key to finishing everything off. The specification that the amber light flashes on returning from stop through to green again, I'd leave the flashing bit right till the end. Get everything else working first, red, amber, green, green, amber, red, and then worry about making it flash. You might want to use your little circuit that you had to go at the other week, where you create a flashing light 1 second on, 1 second off to do that. Alright? So I'm not going to go any further than that. I expect you to build upon the start that I've given you, and you've got some detail about that in this week's notes, and I think they were even included last week as well. So have a go at documenting the program you did around solving the double coiling problem. Let me know when you're ready, and I'll give you the pedestrian crossing exercise sheet, and there's a number of these in the bin at the back. They got the 3 traffic lights there, don't walk, wait, and walk lights on the other side. A push button. Alright? Any questions? Yes. If that was me, I would put those inputs and outputs in straight away, and in this case you kind of also know what each of the M relays do, so I'd probably put them all in to start with so I knew where I was going, yes. And put comments in as I go along as well. Remember, you're likely, particularly with the other program, to be doing that over a number of weeks, and it's about remembering where you got to at the end of the previous week, because you can have a week in between, sometimes more than that if there's a break or you miss a week. So that definitely also helps me. If you ask for help, the comments help me a little bit to understand kind of what you're trying to do with your program. All right?